We got something there? Always good to start with a black screen, isn't it? Okay, so that's what I'm going to talk about today. And so I'm going to pick up on what Matthias said. 97 things every programmer should know. We are currently working on, or about to kick off, 97 things every Java programmer should know. So actually, you may contribute to one more book. It's hard to believe that I was here 10 years ago doing the keynote. It's hard to believe that you were here 10 years ago, because you look so young, and me too. Actually, we're going to talk a little bit about time. We're going to spend a bit of time talking about time. So there's this book, and there's some stuff. Pattern-oriented software architecture, a couple of volumes that I contributed to a few years ago. And the reason this is relevant is because a lot of people misunderstand the point of patterns. They think that they're kind of neat ideas that appeared in a book that was published in 1994. Patterns are actually a little bit deeper than that. The idea of a pattern is the reuse of design knowledge. And not only is it the reuse of design knowledge, it is the model of reasoning that allows you to arrive at a conclusion. You basically, it's an analysis, it's a discussion of the problem and the forces that make the problem, a solution and an understanding of the trade-offs. This is a long way beyond what most people understand as a pattern, but is in fact the original definition of the pattern. And it turns out the patterns originated in the work of Christopher Alexander in the 1960s and 1970s. Now, why am I saying all of this? Because to quote Brian Foote, a member of the patterns community, patterns represent a blatant disregard for originality. There is nothing new. The whole point is that we've seen a solution and we go, I understand why that works, we're going to use it. In fact, when it comes to talking about software development as a profession, a number of times I get people saying, oh, software development's a young profession and, and so on. It's just like, no, it's not. It is not young at all. It's actually quite old. Compared to something like genetic engineering, this is really old. It's not a question of its age. People confuse age with maturity. And as somebody once said, growing old is mandatory, but growing up is optional. And we're not very good at growing up. Software development can only be considered immature because of how we use our experience, not because we lack experience. Millions and millions, we run the planet, basically. Software, we create stuff that ultimately runs modern society. That's not a lack of experience. Okay, let's put it that way. But we're very bad at reasoning about it. So there's this interesting question. I've gone and chosen this term, engineering software, which is simply a reversal of the two words software engineering. And I want to demonstrate how little we've actually learned in the last few decades. So I'm going to go back to the decade of 1960s. In fact, 1960s. Sam just mentioned Jimi Hendrix, my favorite guitarist of all time. And it's just like, yeah. So let's see what is still with us since the 1960s. How much has the world changed? We've still got the Rolling Stones. Hey, we live in fear, again, of nuclear holocaust. I think it's so nice, because I grew up during the Cold War. This was a big concern. And now my children get to have the same benefit. Everything in the 1990s, we thought, well, that's done. We're good. But no, it's back, so they can live up. They can grow up with the same fear through their adolescence as I did. I think it's wonderful. It's nice to be able to pass these things on. What else do we have in the 1960s? Me. I'm the little one there. So I showed this picture to my kids, and it's just like, Dad, was it all black and white back then? It's like, yeah, that's how we looked. We didn't get color until the 70s. So what else was big in the 1960s? Oh, I don't know. Functional programming looked like it was going to be kind of interesting. Oh, so that's changed a lot. Sometimes people talk about Lisp as if it were a 1950s language. I've done a little bit of rooting around. It was specified in the 1950s, but the first working Lisp system wasn't until 1960, and this is my copy of the Lisp 1.5 Programmer's Manual, which is 1962. It's a wonderful book, in the sense that back then, you couldn't just distribute stuff over the internet. If you wanted to distribute stuff, you actually had to tell people how to build it. So this is not just a programmer's manual. It tells you how to create a Lisp machine, which is quite cute. So you've got the full guide there and all the rationale. And 50 years ago, this year, was the software engineering conference, the NATO Software Engineering Conference in Garmisch. And this is, a number of people think that this is a very significant event, but a number of people have misrepresented it, and I've noticed that. I actually went and started reading the original report, and I found it one of the most depressing things I have ever read. Not because it set us on the wrong path, but somehow we did end up on the wrong path. A lot of people credit this conference with creating the term software engineering, but no, that's this woman, Margaret Hamilton, who led a team that developed the Apollo guidance software. As she said, I began to use the term software engineering to distinguish it from hardware and other kinds of engineering, yet treat each type of engineering as part of the overall systems engineering process. She had a very holistic view of what this was about. And certainly back in the 1960s, there was no sense that software was respected. I mean, it's hardware that gets you to the moon. That was the vision. And I'm not going to spend the whole time debating, is it or is it not engineering. I'm going to borrow this idea that taps straight into the thinking that I just presented in terms of patterns from Glenn Vanderburg. A capsule definition of engineering, independent of any discipline, as you're likely to find, the set of practices and techniques that have been determined to work reliably through experience. So that is what we've got. So how much experience have we got? What have we actually learned? Well, if we go back here, then we might say, well, look, software engineering, as maybe you were taught it in university, that was all about big upfront design. It was all about a planned process. We're going to blame these guys for that. The design process is an iterative one. That's in the 1968 document. Okay. In fact, the word iterative occurs quite a lot, as indeed the words unit test, modularity, middleware. Conway's law gets referenced, as does Christopher Alexander, the inventor of patterns, and the use of the word declarative. So, yeah, we've done really well in the last 50 years, inventing all kinds of stuff. So let's look at that development process. Brilliant quote from Douglas Ross. The most deadly thing in software is the concept which almost universally seems to be followed. This was said in the late 60s. That you are going to specify what you're going to do and then do it. And that is where most of our troubles come from. Wow, the world has really changed, hasn't it? Agile development was a big revolution of thinking. There is no essential difference between design and production, since even the production will include decisions which will influence the performance of the software system, and thus properly belong in the design phase. Even Dijkstra was saying stuff, oh, you want to convince the users or yourself that the product is good, it's closely intertwined with the design process. Oh, and of course, we mustn't forget testing. A software system can best be designed if the testing is interlaced with the designing instead of being used after the design. There is not a single piece of advocacy that, I found it utterly depressing that what I've managed to advocate for most of my professional career is not new, and continues to be not new. In fact, it continues to get older. That's the thing that's slightly depressing. I heard this theory that some children think that birthdays make you old. Actually, I like the other interpretation, that it's age gives you birthdays. It's a survival number. Okay, yeah? So, you level up. This is great. But this is really depressing. So let's go and have a look at some language design, and then let's do some testing. So let's see, 1968. Algol 68. So let's write some code. Algol 68. Algol 68 is the most influential language you've never used or probably even heard of. It was considered to be too complex at the time to implement. They actually had to sort of strip it down a little bit, and so the revised report in 1974 is the one that people normally use. It was considered to be too large and too complex and reveal more, and to have characteristics some people would say are designed by committee. I've read the report. It's smaller than Java. It's cleaner than Java. It's more consistent. It doesn't have the same levels of astonishment. It's like, wow, okay, that's kind of interesting. So let's have a look at what this language looked like. Proc, it's a procedure. You can put spaces in your identifiers. Int year, so that basically means we're going to return bool and int. If you ever wondered where all these short words, int and char and all the rest of it comes from, they all come from Algol 68. That was the language that introduced them. Everybody else was using old-fashioned ideas like the word Boolean, which somehow Java picked up instead of following the 68 tradition. You can actually define the whole body as an expression, if you'd like. And that's an automatic return. I'm going to classify whether or not a year is a leap year. It's one of my favorite simple problems. And what we're going to do is we're going to test drive this. So I'm going to create a simple test harness. So what we're going to do is I'm going to create an array of propositions, a leap year spec. I'm going to compose a structure just freely. Years not divisible by 4. I'm going to bind void, if you ever wonder where void came from. Ultimately, it came from Algol 68. I'm going to attach a piece of code. So you call that a lambda. It's a freestanding procedure. So let me think. So Java, when did Java actually become object-oriented? Java became object-oriented in 2014 because up until that point you couldn't treat methods as objects, so it wasn't actually technically object-oriented. But this is not an object-oriented idea. It's not even a functional idea. It's called programming. It's a fundamental programming language idea. So this is 1968. Well, let's build this up. I'm going to use a test-first style. Years not divisible by 4 are not leap years. Here's the structure. This is where the word struct came from, if you use a language that uses that. What else are we going to do? I'm going to test it. That's how you call it. This is a for loop. It's nothing too exciting there. Then we're going to build it up. We're going to actually do some work here. Years divisible by 4, but not by 100 are leap years. So we're going to grow the algorithm or the formula here, and we're going to do that. So that's quite nice. So that's a very declarative approach. Now, I'm not going to say people were doing this back then. They weren't. But they could. We're going to come back to something else that we are going to find is old. I can even create a more DSL-like approach. I can parameterize my, I can create a testing framework that parameterizes this really easily. So let me think. JUnit 5, we can now do that, finally. So what have we got? With 2017, 2001, 1967, and 1, expect false from that result. I'm going to change the definitions. I'm going to change the test driver. And I want to point out a few things here that are kind of interesting from the point of view of regular mainstream imperative language design. That's a little unusual. Algol 68 didn't use dots. We all use dots now. That's kind of interesting. So you can declare anywhere. So let me think. Java started off with this, but this is, as an idea of you can declare anywhere, really didn't become popular in mainstream languages until the 1990s, thanks to C++. So we've got that. The ability to declare within a control structure. This, for some people who use Go, they're very excited by this 1960s feature. The plus equals operator, although it ended up with a few extra characters, that's where this comes from. That was Algol 68. And you can also use if statements. You can use an if as an expression. You can just freely put it in there. So, yeah, and if you can also abbreviate it if you want, but you can use the long form. So this was all available to you in a programming language that was considered to be the next and final programming language. Whenever people do that, they're always wrong. But nonetheless, it is surprisingly regular. And you may criticize the fact that I've just used a test-first approach and say, well, actually, they didn't do that in the 1960s. You'd be right, that was the 1970s. Alfred Ahold, in describing the approach that they used for developing the awk scripting tool, one of my favorite little languages, we instituted a rigorous regression test for all the features of awk. Any of the three of us, Aho, Weinberger, Kernighan, AWK, who put in a new feature into the language, first had to write a test for the new feature. There you go. Test-first programming, 1970 style. So how are we doing in terms of the practices that we've invented? Now, a lot of people, I'm not going to say we knew everything back then. We certainly didn't, and we lacked a lot of the experience, but these ideas were around. And a lot of people now, when I point this stuff out, they say, yeah, but I've got a really powerful computer, and I've got a big screen, and people are still using punch cards sometimes. And I say, yeah, you've just described the hardware. You have not described the software. You've just described the improvements in your environment have all come about through the hardware. And software, all the ideas are just sort of sitting behind a dam, waiting to come through. So let's have a look at this idea. What else was invented back then? Well, it turns out this is not immediately obvious, and it was Glenn Vanderberg that pointed this one out to me. Alan Perlis, there is no such question as testing things after the fact with simulation models, but that in effect the testing and the replacement of simulations with modules that are deeper and more detail goes on with the simulation model controlling, as it were, the place and order in which these things are done. He's describing the work of Brian Randall. He is describing what we now call mock objects, which were not formally invented until 1999 outside Archway Station in North London. We actually have a date and a location for where they came along. All our concerns of abstraction and modularity as well. Barbara Liskov, who won the Turing Award in 2008, she was one of her major contributions was programming with abstract data types. This is from a paper in 1974. A programmer is concerned only with the behavior which that object exhibits, but not with any details of how that behavior is achieved by means of an implementation. That's 74. This is not new. Modularity. David Parnas, he proposed criteria for this. Modularity is a 1960s idea, and he's saying, we have a discipline for this. We propose one begins with a list of difficult design decisions, or design decisions which are likely to change. Each module is then designed to hide such a decision from the others. So in other words, he was acknowledging things like rate of change. He was acknowledging the concept of stability. Only relatively recently have people started focusing on the idea that things may not be stable. I remember when Java came out, I remember the package naming mechanism. And I remember thinking, this may be one of the dumbest ideas I've ever seen, but I can't quite tell why. And then I realized, internet domain names are not stable. What you find is that most software lives longer than the company that creates it. I would refer you to Sun Microsystems. Yeah, so in other words, if you are using your domain name as your package name, what you're doing is you're anchoring the whole naming structure, the whole naming space, to one of the least stable concepts outside of your control. You have failed to encapsulate it. So there is a point here. We know this stuff. We should understand the concept of stability. And then we had this idea that was kicking around, structured programming. Again, a lot of people think structured programming is programming without go-tos. But if you read this book, you'll realize it's got a section in the back all about object-oriented programming, because objects and classes were considered structure, concept hierarchies, what we now call class hierarchies. All this is there. It might not be perfect, but it's all there. It's all really old. So where does that leave us? It leaves us on Salisbury Plain. I took this picture a year ago because my wife and I are clearly incredibly romantic. On Valentine's Day, we decided, okay, let's grab the kids and go and see Stonehenge, because that's what you do on Valentine's Day, right? So I got this nice picture, and my kids were really impressed. They'd seen photographs of these stones, and they said they really are much bigger in real life. I had to take a picture because I suddenly realized, you know what? This is the Greek monolithos, monolith, monolithos, one stone, one big stone. This is enterprise development, 2000 BC. We're going to create these huge, great, big stones, and they actually built it. Now looks like they built it in Wales and then moved it to Salisbury Plain, that's such an enterprise thing to do. It's just like, yeah, okay, well, actually, we're going to move offices now. Yeah, and it's just like, and you're working with code like this. So all the dreams of this beautiful engineering model, and you've ended up with one big stone. And yet we know that we want it to look like this. This is how we want to arrange our stones, intentionally, elegantly, with beauty. Again, this is not a new idea. This is a modular concept, and these ideas date back. Doug McElroy, who was also at the Software Engineering conference, described this as the Unix philosophy. Write programs that do one thing and do it well. Write programs to work together. Now, the funny thing is that there's been a shift in people's perception. Whenever I use this quote now, I've used this quote for a number of years, and a lot of people now immediately look at that and go, oh, I know what you're talking about. You're talking about microservices, aren't you, Kevlin? And I say, well, if it makes you feel comfortable, yes, I am. Okay? And people go, well, you know, microservices, yeah, that's a really kind of new idea. Well, in many ways, not really. It's just that we've reached a particular point where the hardware can support most of these things. The concept of the network, the processor speed, this all amortizes the cost of process creation. And it reduces the question of communication, because we've got higher bandwidth. But when we come to talk about microservices, we're not simply talking about modularity for its own sake. We're not talking about it in terms of abstraction, as we were with, say, Parnas and Liskov. We're also talking about the idea that microservices create a new model of development. In other words, we have this idea that the microservices reflected into the real world will influence how we organize our teams, how we organize our business, how we organize our activities. So clearly this is a new idea. So back to 1968. Define a subset of the system which is small enough to bring to an operational state, then build on that subsystem. E. David also goes on to say how long this should take, which is a few months, with a team of maybe no more than 4 or 6. This strategy requires the system be designed in modules which can be realized, tested, and modified independently, apart from the conventions for intermodule communication. So yeah, there we go, microservices. But we are confronted with this problem. There you go. That's what you've ended up with. That's your microservice architecture. Again, this was foretold by Alan Perlis, who was the first recipient of the Turing Award. In the long run, every program becomes Rococo, then rubble. So we're not doing particularly well. So are there some other ideas there, perhaps that post-date the 1960s? Well, yeah, let's look at the late 1980s and early 90s. There is this perspective that as systems get larger, simply programming them is not the right way of doing it, because there is a natural limitation. It comes from team size and organization. Again, we knew this because Conway published his paper on how organizational structure influences software architecture. He published that paper in 1968. Dave Galento and Nicholas Carrera came up with an approach for organizing concurrent systems, which has kind of fallen by the wayside. It inspired Ginny, but there is a deeper idea in what they were describing. They talked about coordination languages, and it's a philosophy of architecture I think is particularly attractive, and it is sort of, we are recognizing its value once again. We can build a complete programming model out of 2 separate pieces, the computation model and the coordination model. In other words, there is this idea of sort of trying to capture the orchestration in some way and say, well, okay, look, let's just look at the programming side of it, the small tasks, the small, simple, this does one thing well, and then arrange them together. These small pieces are easily unit testable, because it would be really stupid to develop a system without that, because then you wouldn't be able to unit test it. You would end up with a legacy code base. So there's a kind of an obvious philosophy here. But it is not simply a way of thinking about your architecture. It is also a philosophy that applies at the statement level. We can see this concept of coordination model. Historically, the coordination model that people have worked with is sequence. In other words, this statement follows this statement. Okay? And they've got branching with an if and repetition with a while or some variant of a for loop. That is a very simple coordination model. And it turns out one of the attractions of having things in sequence is that human beings can think in sequence. We think, we reason about things very clearly when they are sequential. But there's more than one kind of sequence. There is control flow sequence, but there is also data flow sequence. And this has a number of other benefits. So I want to refer to this cheat sheet that Zero Turnaround released 2 years ago. Their cheat sheets are really useful, and this one's the Java 8 Streams cheat sheet. And I remember when they mentioned this, they listed it on Twitter. I went and looked. I thought, oh, that's quite useful. And I looked at the stream examples section, and I thought, there's a mistake. So then I tweeted, this needs, you've got this wrong. So then they fixed it. Unfortunately, they Well, technically, I guess what they did is they incorrected it. To take something that, they didn't correct it, they incorrected it. It's still wrong, but it's now, excitingly enough, differently wrong. So let's just actually go through what is going on here, because you can see there's a very different coordination philosophy here than the conventional imperative statement control flow structure. What we've got here is a flow structure that is data-oriented, stream-oriented, pipeline-oriented. And in it, we compose small pieces. It's this composability that Galante was talking about. It's this composability that was attractive originally with the Algol 68 philosophy and the Lisp philosophy. It's this composability that inspired people to create original object systems. The problem is many of our systems become monolithic. They defeat that composability. About the only thing you can make out of large stones is Stonehenge. And then, in other words, it becomes a monolith and a burial ground for enterprise. So let's have a look at this. What is the brief? Get the unique surnames in uppercase of the first 15 book authors that are 50 years old or older. Does it do this? Well, let us assume a library is a collection of books, and we're going to stream it, and we're going to map it. We're going to take each book, and we're going to get the author. And then we're going to filter in, so we're going to select. I tend to prefer the terminology select. Filter is, well, they're all filters in the kind of classic pipes and filters terminology. Select is more specific. Author, we're going to take an author, and we're going to filter all authors that are 50 or over. So that would be, this point in 1968 and earlier. We're going to limit that to 15. And then we're going to get the surname, shift it to uppercase, uniquify it, and then we're done. The problem is this doesn't do what the brief says. The specification that actually matches this is get the unique surnames in uppercase of the authors of the first 15 books, which is slightly different. If you've got 15 books all written by the same author, then that's not quite what you were after. So we need the unique authors. So then they incorrected it to this, which gets the first 15 unique surnames in uppercase of the book authors that are 50 years old or older. So we've got the same mapping, the same filtering, then we get the surname, shift it to uppercase, uniquify it, and bound it to 15. Unfortunately, that's the first 15 unique surnames that we encounter. That's not quite right. It turns out that to get it right, you have to uniquify it in two places. Get the unique authors. We could actually move that up if we wanted. That makes no difference to the outcome. Limit it to 15, get the surname, shift to uppercase, now uniquify it. Now it finally meets the spec. Now what is the point of all of this? The point of all of this is that it is easy to read. This is the appropriate coordination model for this task. It is naturally a flow-oriented problem. In fact, quite a lot of problems are much more flow-oriented than we give them credit for, but we get lost in the control flow. And what I find valuable is that it is easier to see that it is wrong. It is actually easy to take a non-Java programmer or somebody unfamiliar with the Streams API and walk them through it verbally, and they'll understand it and can fix it at that level. In other words, it presents itself. It's about comprehensibility. It turns out that is one of the things we've really been trying to strive for. That is one of the benefits that we've been able to get with changes of hardware, is the ability to say it's okay to have identifiers that are longer than 6 characters. That used to be the kind of standard upper limit for systems. You can make them actually much more comprehensible. So there is this, so if you've ever wondered, by the way, talking about Lisp languages, there is a language called Scheme. It was going to be called Schema, except that 6 characters is the limit. So that's why it's called Scheme. So there is this notion here that this declarative approach, we have matched the programming model, the coordination model. We've got the little pieces of computation. So it works at the statement level. This is not just an architecture model. Now, I presented this at JavaZone in Oslo a couple of years back, and Trisha G from JetBrains really liked the example, because she was focusing on one of her interests is getting people to refactor to Java 8 and beyond. And so she was interested in that, but she said, what would be really interesting is if I had looked, what would the code look like without streams? If I had looked at that first, and I thought, you know what, that's a really interesting idea, so here it is. The first thing you notice is there's not enough space. We're going to need a smaller font. Okay. Now, this perfectly recreates the original version. Can you tell that? Can you tell that it doesn't quite meet the spec? In fact, can you tell what it does? Yeah, of course, you're a skilled developer. Exactly. You're going to sit there and filter through it. What you're doing is the job of a computer. What you're doing is you're actually you're going through, you've got a little program counter running in your head, you're jumping around, we've got a go-to statement there, it's called break. You can say that it's not a go-to statement. It's a go-to statement. It's just spelt differently. Oh, but it's limited in some way. Yes, all go-to statements are limited in some way. That is a deep truth. That's why we generally discourage them. It disrupts the flow, but look what we've got here. What you're having to do is decode this. This is quite literally written in code. Here's the other version that they did. It's not quite right. And here's the version that is correct. Can you tell that? No. I can't walk through that easily and point these things out, because most of this code is about the mechanical housekeeping. Okay, we're going to need to set up a variable, we're going to need to set up, we're going to fire up a loop, and then we're going to do this, and then all the stuff that's interesting is kind of on the inside, and you've got to dig it out. And I'm going to propose and observe that you have undoubtedly written all the loops you will ever need in your life. Probably more, actually. You don't need to write another loop. You've met all of the loops you will ever meet. Okay, you know the loops. There's the loop where we accumulate something. There's the loop where we apply something to everything in a collection. There's the loop where we look for the first instance. There's the loop where we've done them all. You've seen them all. There is not a single new. The only thing that you can do now that it seems new is to take two loop concepts and smash them together and call it enterprise. Oh, this loop does half a dozen things. Oh, I'm going to make it do 7. Cool. That's enterprise development. Yeah, that's it. It's a cocktail. It's a mashup. That's it. So the whole point here is that this streams model is a representation of a coordination model that dates back to 1964. Oh, it's Doug McElroy again. 1964, let me think. That's 50 years before Java got streams. We should have some way of coupling programs like garden hose, screwing in another segment when it becomes necessary to massage the data in another way. And this is the way of I/O also. This is the Unix pipes and filters model. Doug McElroy invented it, but it wasn't until Ken Thompson chose the character that it became real. It took 6 years for somebody to say, you know that symbol, the little line? Yeah, we'll use that one. Yeah. So people always say naming is really hard. There you go. Choosing that one character was a showstopper. But ultimately, what we also see here, and the original motivation for a lot of these different approaches and philosophies, was a way of thinking about concurrency, coordination, because we are limited in how we think about things. We're not very good at understanding multiple occurrences. So we really need to understand how to reason about code that is concurrent. And that is genuinely something that we've had to be confronted with in recent times. The last 20 years, it's become a real thing. So here's the thing that I tend to draw up. I originally drew it up a few years ago in a workshop for one company when we were talking about concurrency and design. And I was trying to encourage them to think quite literally outside the box that they got stuck in. All of their code was based on the idea of basically we're going to fire threads across our code base, and we're going to then synchronize stuff so that it's safe. Yeah, because synchronized is like the word that makes things safe. Yeah, if you just put it in enough places, that should do the trick. And I thought, okay, well, let's be very clear about this. The challenge here is primarily one of being able to reason about your code. It's comprehensibility. So let's draw out a simple quadrant diagram. And as with any quadrant diagram, there's normally something that's really, really good or something that's really, really bad. In this case, it's really, really bad. I'm going to make it absolutely clear which one that is. I'm going to use nature's color of danger. Okay, it's a really strong clue. I had somebody ask me recently, what about people who are colorblind? I am colorblind. I chose shades of red and green that I can see. There is no ambiguity here. Now, in the Far East, red is often used as a color of celebration. That is true for consultants. What we have here is a simple way of reasoning about the relationship of the control flow and the data. At any given point in time, a piece of data can be shared between two threads of control or unshared. We can pass it around, but the point is, at any given point in time, it may be unshared, and we can still pass it around. In other words, it's only ever active in one thread at a time. Or it can be simultaneously accessed by multiple threads. And that data can be considered to be mutable or immutable. We can change it or we can't. Okay, that's it. That gives us 4 quadrants. It turns out all the pain happens up here in the synchronization quadrant. This is where you, as a developer, need to explicitly control. It's your problem. It's not somebody else's problem. It's your problem. And it has to be made explicit. You have to look after it. Now, notice that 3/4 of the territory is quite easy to program in. Yet, like moths attracted to a flame, we are drawn to that top right quadrant. Okay, it's just like, yeah, let's go in there. Life is easy. Let's just not share data. This is actually the original Unix model. The idea is that processes were single-threaded. In fact, Unix was very resistant. If you look through the history of thread adoption through the 1980s and 1990s, the Unix culture was very resistant to the adoption of threads because it already had a way of dealing with breaking things up for concurrent execution. It was the process model. And it already had this isolation. So in other words, we don't share data. I'm going to pass you, using some IPC mechanism, I'm going to pass you something. Now, we might say the problem with the IPC mechanism is we have to marshal and unmarshal. Yeah, it gets a bit messy. The value or cheapness of being able to do it in the same process space means we can have the same programming language, the same program model. Oh, that's really attractive. But that doesn't make it easy. The problem here also is, as we like to observe, what's going on in the top right-hand corner is what are we doing when we synchronize things? What are we doing when we lock something? We are preventing execution. And now in the multi-core era, it becomes far more obvious. When we were faking it all on a single processor core, it was not quite so obvious, but now it's really obvious. And you go to teams and say, well, why have you got all this multi-threaded stuff? Oh, we're trying to make it faster. Okay, so why have you got all these locks? Oh, we're trying to make it slower. Well, they never say that, but that's actually, if you point that out, it's just like what you've got is a lock is the anti-thread. The purpose of a lock is to eliminate concurrency. So if your goal is to improve and increase concurrency, you may find there's a contradiction here. Now, this is not news. There's a lovely talk in 2013 by Brett Victor, The Future of Programming. And he does this lovely talk as if he was speaking in 1973. I didn't find out about his talk until I wanted to start talking about 1968. And it's just like, this is quite an interesting one, because he does a number of the same points. And he says, well, from the point of view of 1973, threads and locks, they're kind of a dead end, right? So I think if we're still using threads and locks, we should just like pack up and go home, because we've clearly failed as an engineering field. And he was saying, if we're still using this in 2013, we should... Yeah, these are primitives. I'm not saying you don't want them. Just as your low-level assemblers have jump statements, we don't like the jump statements. We don't have unbounded go-tos in most modern programming languages at a higher level. It's a very powerful construct, but it lives down here. The whole point of this like layered view or abstracted view is that we take that stuff out, that we try and capture our intent, that I don't sit there putting together little control flows. I'm going to have a while here and a break here for something that is quite clearly filter on a set of things that come in sequence. This is commoditized. So there's this idea that somehow we've missed a really fundamental trick here. So what have we got? Computation model allows programs to build a single computation activity, a single-threaded, step-at-a-time computation. We can fit it in our heads. The coordination model is the glue. This idea of the glue language, this terminology is also quite old, and you bring these things together. And the coordination model I've just looked at is relatively straightforward. And what we've got is a channel, a pipe, and you can have it of a particular size. It can be bounded, buffered, asynchronous. If I make n infinite, then it's unbounded, buffered, and asynchronous. Don't have unbounded queues. The world is finite. It's generally a good idea. Normally when people prototype things or show demo examples, the queues are ultimately unbounded. You don't want unbounded queues. This is very bad. In the absence of infinite memory, which unfortunately we've not yet been able to solve, this will cause you problems. So we tend to bound them. We also have special cases. If we have a bound of 1 and we pass it around, then that's a future. If you can model a future exactly as a bounded channel of one element. If we make it a 0 depth, then that gives us a synchronous channel. And a lot of people, again, in Go have got very excited about this idea that was introduced in the 1970s by Tony Hoare. Communicating with sequential processes. The model here is a functional way of looking at concurrency based on named channels. And so everything is sequential because we work with sequential, and yet you have high concurrency. I was lucky enough in the land before the web to do a master's degree in which my thesis was based on an actor-based concurrent language, ABCL. And that, I thought that was going to be the future. That was going to be the future. And then finally in the 21st century, other people have woken up to the actor model, which was invented by Carl Hewitt in 1973. We're finally getting around to it. Although I would question some of the stuff that I've seen in terms of the Scala world. It's like, yeah, that's probably not what they meant, but that's a detail. But the idea is that finally we seem to be getting all of these really old ideas kind of sorted out. And so people keep adding stuff that is relatively new, or rather, people feel is new. So going back to 1978, another Turing Award winner, Robert Floyd, he's the guy we can actually blame for getting us all talking about the word paradigm. It's his fault. He introduced the word paradigm to the software world. Paradigms of programming. I would strongly encourage you, if you're going to use the paradigm word, to read this paper first, because you might not use it afterwards, or you will use it with a little more caution. And actually, it turns out a lot of what he talks about is what we would now call patterns. But he has this lovely observation back in '78. I believe the current state of the art of computer programming reflects inadequacies in our stock of paradigms, in our knowledge of existing paradigms, in the way we teach programming paradigms, and in the way our programming languages support or fail to support the paradigms of their user communities. This goes right back to this idea that I need to find the shape of the problem and then express it. The idea is that we have experience. Oh, this is one of those problems. It should look like this. I want a programming language that supports that, or I want a programming view. At the moment, we keep bandwagoning onto what we consider to be new paradigms, but at best, they are reblends of old ideas. To put it another way, we haven't really done much that's new. What we've done is things have become new to us, but they are not genuinely new ideas. This is slightly depressing. In fact, that's what I say. Looking back at the history of programming and its development and team structure and development process has been a little bit unnerving for the last couple of years while I've been doing it. So is there anything new? Is there anything that actually is not just a rehash of basically everything that's going to happen in most every programming language you're working with has already been invented and somebody's already tried? There is nothing new that you are going to experience. But the future is already here. I'm not going to predict the future, but I want to show something, a couple of things, think about things that are genuinely different and maybe slightly disturbing at one level. Future is already here. William Gibson noted it's just not very evenly distributed. Okay? All of the programming problems that you have, they're not problems. Somebody has solved them. Okay? Every single thing that you have encountered in your professional career, somebody else has a solution to. The problem is that we don't have telepathy. Actually, I think that's probably a good thing that we don't have telepathy. But the thing is that what we have is a lack of distribution of knowledge. You have the problem, somebody else solved it, you never know this. Okay? So we end up having to reinvent and do the hard work. That's, for me, why things like originally patterns were really important, because they were a propagation of knowledge. Here's stuff that we know. It's, for me, why the idea of open source is particularly valuable, because you're able to say, let's put this out there so everybody can see it. It doesn't mean they will guaranteed to be they're guaranteed to find it, but if you don't put it out there, they're guaranteed not to find it. So, in other words, you increase the probability that things will arrive. So, If I were to think about architecture, in software architecture, we have a number of criteria. We value things like modularity. We value clear structure. So in 2011, somebody did an analysis of the structure of bacterium, E. coli, and they also did a structure of the internal structure of Linux kernel, the call graph. I think this is quite interesting because it shows you what nature looks like versus versus what designed things look like. Nature is very different. Nature doesn't really believe strongly in modularity the way that we do. It does not believe in single responsibility principle. It does not believe in cohesion and all these things. What you see is that in the Linux call graph, you've got this fan-in. It's got this idea of, there's a reuse idea, but nature's idea of reuse is kind of weird. It's got a very different structure. If you look on the left, there's a lot more redundancy, and it fails soft. In fact, there's a sort of I like the way that it's been drawn. It's a very physical metaphor, because if I were to actually 3D print these shapes, which one would fall over most easily? The ones we build. Nature is kind of like resilient. It's not perfect. Yeah, some of you have undoubtedly experienced the exciting flu that has been going around. Clearly, it'd be nice if that didn't happen at all. The fact that we're able to recover at all is the most impressive thing. The human body is surprisingly resilient. Most life is resilient at one level. It's not perfect. We make mistakes. This is an absolute mess. Good grief. I mean, it's the most hacked thing that we could ever study. The human brain is just, to reverse engineer it, it's a nightmare, because a software developer would never develop something like that. Unless they were in an enterprise environment, yeah. Okay, so enterprise development as Darwinism. I'd never thought of that. Okay, so the point here is that nature doesn't look like the things that we build, and yet it has a number of valuable properties. Now, what's that got to do with anything? How are we going to build this stuff? So this is from 3 years ago. This is kind of interesting, because this is from a company that has optimized 3D printing for, this is a bracket, to bare load. Okay? Now you can spot the one that's designed by humans. That's kind of easy. It's designed by humans that way so that we can understand it, so that you can apply simple principles, calculate through. That's the one on the left. Machine learning gives us the one in the middle. That uses far less material. And this company just did this one on the right. It carries the same load, and yet it uses a fraction of the material. Can you tell how it works? Could you maintain it? That's interesting, because I can tell how the one on the left works, and if somebody said we need to change something, I can tell how I would change it. But that's not the stuff on the right, which has been optimized via a very different route. So, okay, that's physical stuff. What about software? What if people are getting very excited by machine learning at the moment, but at the moment they're looking outwards. They're looking to, where can I apply machine learning in the world of the user and their application domain? And I would like to urge people in software development, as with many of the things that we've done, look inwards. What happens if you take those ideas and apply it to the stuff that we do? When I was younger, one of the things that seemed incredibly obvious to me, there was a whole phase that we were all going to get into expert systems. That was the future of AI. But it seemed blindingly obvious to me that one of the things that we should have expert systems for was debugging. And yet I never saw anything. It was always about other people's domains, never our own. And so I'm going to try and say, well, maybe we should be doing this with ourselves. Oh, it turns out we are. Interesting paper. It's not yet been published formally, but it's still in preprint. The case for learned index structures. This is last year. Learned index structures, machine learned index, all that data structures and algorithm stuff looks completely different now if you look at it like this. Our initial results show that by using neural nets, we are able to outperform cache-optimized B trees by up to 70% in speed, while saving an order of magnitude in memory over several real-world data sets. So in other words, now what we're going to do is, we're not going to have linked lists and B trees and bits and pieces like that. Even collections. It's a case, look, I've got some examples. You learn it. Figure it out. figure out something that works. So in other words, software development becomes really the application of constraints. It becomes ultimately declarative. The idea is that what we do is we say, here's the shape of the thing that I want. Just generate stuff. They go further. More importantly, we believe that the idea of replacing core components of a data management system through learned models has far-reaching implications for future systems designs, and this work just provides a glimpse of what might be possible. We also see it in other cases. There's program optimization tools. When the RISC era came, it turns out that code optimization became counterintuitive. In other words, the instructions that you see are not necessarily the instructions that are executed in the right order. It's, in fact, the joy of the recent Spectre and Meltdown bugs shows you how counterintuitive that is. It also shows you where our problems are. It shows you that it's all very well to say, I want this system to learn this, but there's a huge bias towards the data and understanding what's going on. Because if we've spent most of the last few decades, and I've spent most of my career trying to encourage people to think clearly, your code should be comprehensible. When I encourage people to write tests, your test should be a declaration of your intent, not a description of the mechanics. We can already see the mechanics. Show me what you mean. It's about meaning. It's about communication. Communication between human beings. But if human beings aren't involved in this, then we actually end up with architectures that are now going to be incomprehensible, and we're going to like it, rather than the stuff we see at the moment, which we call legacy code and we don't like. Now, that's kind of interesting, because that changes the whole game. That changes the purpose and sets us in a very different direction. It also highlights something we need to be very careful of. But going back to 1980, Meyer Lehman introduced a really interesting scheme of classification for systems and programs. I find I kind of rediscovered it a couple of years ago. And found it incredibly useful for reasoning. S programs, P programs, and E programs. S programs, programs whose function is formally defined by and derivable from a specification. Pretty much anything that is easily unit testable falls into this category. The idea that, oh, I can specify it, and once you've been told the specification, it's fairly easy to organize objects and functions to do the right thing. Okay? Business logic, yep, that looks like this. Okay, there's really nothing really surprising here about these. It turns out most things can be decomposed in a modular fashion to S programs. But it's the integration into stuff like P programs start getting interesting. P stands for, we have a procedure to recognize a good solution, but I couldn't necessarily tell you what that solution would be in advance. So in other words, I can tell you the rules of chess, but it's not entirely obvious how to build an effective chess program just being given the rules of chess. But I can tell you that I can classify a successful chess program. So I can test for it, but I cannot necessarily say how we're going to develop it. The architecture is less obvious even when I've told you the paradigm. Whereas with S programs, if I give you a problem and I give you the paradigm, there's clearly intellectual work involved, but it is not going to be as exploratory as this. Now it gets more interesting. E. E programs, programs that mechanize a human or societal activity. The program has become part of the world it models. It is embedded in it. E is for embedded or environment. Now what is interesting is that when Meyer Lehman wrote this back in 1980, there weren't that many systems that would be considered E-type systems. E system, in fact, the example he chose was air traffic control. Because the output of the air traffic control goes to a human being who then relays it to the pilot of a craft that then maneuvers the craft accordingly, which then becomes the input the next round. In other words, you have changed the world. The software is now part of the system, truly. Most software that people produce now ends up being used in E-type systems. It becomes part of the world and changes the world. Its output will then change the world. We've seen this whether we're talking about elections, whether we're talking about marketing. We've seen this in terms of what happens when there are security breaches and so on. There is a huge consequence here. And this starts telling us, well, you know, maybe we need to be a little more careful. Particularly when we start saying we want more machine learning for ourselves as well as other people. So this gets us to, this is one of the things engineers often like, a system of ethics. And in fact, the Association of Computing Machinery, which I'm a senior member, the ACM, is currently working through coming up with a code of ethics and professional conduct. Very interesting. And there's quite a lot of stuff about that reflects very much the times that we're in. Observations: the actions of computing professionals directly impact significant aspects of society. We run the world, as I said earlier. In order to meet their responsibilities, computing professionals must always support the public good. Now, if we've just said that our systems are beyond our understanding, even when we engineer them in the way that we thought was good, they're going to become even less comprehensible over time. That kind of suggests that testing becomes the most important thing. Testing is a definition of constraints. That becomes, and indeed, in 97 Things Every Programmer Should Know, Neil Ford observed that testing is the engineering rigor of software development. There is this idea that there is the completeness there of being able to have confidence in the thing that has been created. But we also need to be very careful. Just because something is testing does not mean it is automatically ethical and good. Many people use A/B testing for websites, and the idea of A/B testing is that we present users, depending on who they are, with one version or another, and we see the difference in their response. And the good side of this is clearly, if people seem to disappear off the version A and spend more time on version B, then we would say B is better. In other words, they're getting a better experience. Or, more to the point, conversions. If people are buying the goods or buying the services or using the services in one version but not in the other, then clearly the user interface offers us a better approach. Or, in fact, it goes deeper than the UI. The supporting software itself is better in some way. The problem is, we need to be very careful with this, because this experiment was run by Facebook a couple of years ago. I'm just picking on Facebook. This is a 2012 experiment. I'm just picking on Facebook because everybody knows about them, and a lot of people often go, well, we're not Facebook. We're all good and stuff like that. I use Facebook. We show via a massive n equals 689,003. Basically, that's 700,000 people were involved in this experiment, and they didn't know it. On Facebook, that emotional states can be transferred to others via emotional contagion, leading people to experience the same emotions without their awareness. That's a little bit scary. It turns out that at scale, we can influence how people think, which is exactly what this is. A/B testing is whether or not we can empty, in many systems, can we empty people's bank accounts more effectively? And there's a very interesting ethical question there, which I'm totally not going to answer, because I don't know the answer. But we need to be very aware. When people start talking about engineering, they start talking about bridges collapsing and saying, well, we don't have that in software. Well, maybe we do. Maybe we do. This is a very interesting question, to which we have the old Spider-Man adage. With great power comes great responsibility. If you're going to run the world, you better be a little cautious about it. So we need to be careful and somewhat alert to the fact that when we talk about software engineering, it is also social engineering. And that was not something a lot of people signed up for. They find themselves having enjoyed the technical side of things, but then suddenly they find themselves in a much, much more complex world. And one of the things I've been talking about recently, people have been talking a lot about full-stack development. Now, I have a couple of comments about full-stack development. I've seen it, people sort of say, I've seen it in their Twitter bio, I'm a full-stack developer. Every time I've ever talked to a full-stack developer, it turns out they've never done device driver development or kernel work. I mean, I know what the stack looks like. I've drawn them, standard, it goes all the way down. It touches the metal. That's what the stack includes. But there's another direction as well. It's not just it goes all the way down. It goes all the way out as well into the world. And I think people are not necessarily prepared for that. And so we have this big challenge. It's a challenge of knowledge and challenge of observation. The challenge of knowledge is there is surprisingly little under the sun. That should not stop you enjoying programming. I quite enjoy programming in new languages that use features that were introduced in the 1960s. It's quite pleasant, just as I enjoy listening to Jimi Hendrix. Okay? I kind of like, old-fashioned programming, like using Java and Haskell and stuff like that. These old languages, these old ideas. It's quite fun playing around with them. But we also, and you can do practical stuff with it. But at the same time, don't kid yourselves that it's new and exciting. It's just, it's genuinely, this is where perhaps some of the engineering stuff comes in. It is the stuff that is tried and tested at some level. That's why perhaps, if we're being optimistic, why perhaps we're still using it. Perhaps why the rate of adoption is so slow. We can be less cynical about it perhaps and say, no, we're building on firmer ground. But it turns out the missing ingredient is us. And that's what I'm going to leave you with. Thank you very much.